Let's talk about the hysteresis loops that we observe in ferromagnetic materials. First thing I would like to do is to introduce the concept of a soft magnet versus a hard magnet. So if you look at the initial magnetization curve, M versus H, so starting from a demagnetized state, we apply a magnetic field in order to magnetize the material. We see that some materials will require a relatively small amount of magnetic field to reach the saturation magnetization, and some materials would require a much larger magnetic field to reach the saturation magnetization. So, if a material requires a small amount of magnetic field to reach saturation, we call it soft. So the first one here, A, is a soft magnet. So this is a soft magnet. On the other hand, if you look at C, for example, this requires a relatively large field in order to reach saturation. That we would call a hard magnet. So that's basically the main idea. So if you want to look at B, well, B is harder compared to A, but softer compared to C. So that's basically the terminology we use. So we can say that if a small applied field is sufficient to produce saturation, the material is said to be magnetically soft. For example, nickel 81, iron 19 permalloy is a soft magnet. On the other hand, if the saturation requires very large fields, then such a material is magnetically hard. Permanent magnets fall into this category. For example, neodymium iron boron. Permanent magnets, they are very hard to magnetize. All right, so about this magnetization curves of different materials, we said that we can have magnetization versus magnetic field or magnetic induction versus magnetic field as the magnetization curve. There is one difference between these two, so let's put a remark here. If you go to saturation, the magnetization is going to be a constant value, ms. So this will reflect as a constant, not changing m value for a relatively large magnetic field. However, if you look at the corresponding magnetic induction versus magnetic field curve, after saturation, we will see that there is still a slope in the dBdh. So while we see no effect of permeability in the magnetization, because we have a permeability in the material, it's going to affect the slope beyond saturation. So, but if you're using CGS units, the slope will be basically 1. So it will be linearly increasing with magnetic field. So let's note that here, although we see that the magnetization M is constant after saturation, if we look at magnetic induction, B will increase with H beyond saturation. And why is that? Well, you will have dB dH is equal to 1 in CGS units, or mu in SI units. So after reaching the saturation induction, we're going to see for B greater than Bs, we're going to see still an increase in the magnetic induction with the applied magnetic field. Now I would like to concentrate on the hysteresis loop fully. So first of all, I would like to saturate the magnet starting from a demagnetized state. So let's put a procedure here. So first I'm going to start in a demagnetized state. We're going to talk about how this demagnetized state is obtained in the next video. So demagnetized state, the total magnetization is 0. What we will do is we will increase the magnetic field H to saturation, so that we will have M is equal to Ms, saturation value, and that is basically called saturation magnetization. And also B will become Bs, that is saturation magnetic induction. Okay, so how do we achieve this? So starting from the demagnetized state, so let's look at what happens. If we're looking at the BH curve, we will see that this is going to follow a path like this. We're going to go to the saturation value of the magnetic induction, and the corresponding M versus H will give us this curve where the Ms value is not changing afterwards. However, magnetic induction has a slope, a small slope, due to the permeability, the non-zero permeability. So we see that these values of Bs and Ms will correspond to the same magnetic field where we have the phenomenon of saturation. So we are at Bs and Ms beyond saturation. Bs value is the value that corresponds to saturation magnetization, the field that produces saturation magnetization, and we can call this field the saturation field, H saturation. Okay, Now this curve that this magnet is following, starting from the demagnetized state to the saturation, is called the normal induction curve. All right, so the magnetization curve the red curve, which is from the demagnetized state to saturation, is called the normal induction curve. Okay. Now, sometimes we will see that instead of plotting B versus H, they will plot B minus H versus H. So this is usually done in CGS units. So let's put a remark here. Sometimes in CGS units, we will see that the intrinsic induction is defined as the difference between magnetic induction and the applied magnetic field, is plotted as a function of the magnetic field. And since we have B minus H is equal to 4 pi m, this differs from m versus h by about a factor of 4 pi. So we see a different B value, that's the intrinsic B that is plotted against H. Now we continue our story. So the third step, what we will do is we will reduce the magnetic field to 0. So if H is reduced to 0 after saturation, what will happen? We will see that the induction in the specimen decreases from the saturation induction Bs to a value Br, which is called retentivity or residual induction or remanence. The Turkish word is atık. Atık mıknatıslanma. Okay. So let's see this process now. We have reached the saturation. Now we're going back to 0 magnetic field. So that appears along this path. So we have reached saturation. Now we're going back to 0. And what we see here is this residual induction Br value. So even though the magnetic field has been decreased to 0, we still have retentivity, residual induction, or remanence. Now, as a fourth step, if H is then reversed, if we apply a negative magnetic field, what will happen? The induction will decrease to 0 when the magnetic field H is equal to Hc, called the coercivity, or an unfortunate name, coercive force. An unfortunate name for magnetic field was magnetizing force, and therefore this coercivity also has an unfortunate name, coercive force, which is sometimes used. Now, if that's the case, what we will see is that magnetic induction is going to be 0 when we have Hc plus 4 pi m, if you wish. Well, this is actually not quite correct if we're not in the initial induction curve anymore. So what I would like to point out here is that when the saturation magnetization becomes 0 is not at the same point as the magnetic induction becomes 0. So if you assume that we have this constitutive relation between H, M, and B, you would see that M would have to be Hc over 4 pi when B is 0. Once again, this is actually not quite applicable in this range where we have this hysteresis loop. But anyway, the idea is that the magnetic induction and the magnetization are not 0 at the same field. So that means we may have to define two types of coercivity. So we can say that the reverse field that is required to bring the magnetization M to 0 is called the intrinsic coercivity. So this is denoted by HCI, or we can say that there is an HC for B and there is an HC for M. So these two are not the same. Once again, this linear relationship between B and H obviously does not apply when we are going through this loop. However, it does show that B is not 0 when M is 0. So going through this step, we reach the coercive field Hc. That's the field at which magnetic induction is 0. Intrinsic coercive field is when the magnetization is 0. Okay, so there is a distinction between these two. So after negative saturation, so if I continue with this, I reach a negative saturation. So you can see here, if you follow this, I go to negative saturation, minus Bs, and then I'm going to go back to 0, and then to positive saturation, the hysteresis loop that I have obtained here is called the major loop. So basically I have completed a full saturation between plus BS and minus BS, and I have achieved a major loop. However, if I disrupt this process, let's say that I have come to this point A and then I have decided to reverse the field, and then I come to this point D, I reverse the field again, and I have another loop here which is now called the minor loop. So this is going to be my minor loop, and this loop, the complete loop between saturation values, will be my major loop. And you can see that while tracing the major loop, I also reach a minus retentivity in the process. So that's the distinction between minor and major loops. So in the fifth step, I go to negative saturation. After negative saturation, if the field is increased back to positive saturation, the loop that we trace out is known as the major loop. On the other hand, we also call this major loop or major hysteresis. If I interrupt the process, if the process of initial magnetization is interrupted at some intermediate point, you will see that, and then the field is reversed and reapplied. The induction, the magnetic induction, will travel on a path following a minor hysteresis loop. Now you can see here that when I'm tracing a minor hysteresis loop, I also have a remnant field here, BR. Let's call this BR prime for the minor loop that I have chosen. And there is also a coercive field that's at point C, HC prime. Now this process could also be interrupted somewhere else. For example, if I interrupted at point G, I go to point F and then come back to point G. There is another loop that I'm tracing here. So basically I'm pointing out to this loop. There is another loop I can do here while performing the negative saturation. I can stop the process and do this. And basically all of these processes will give me a minor loop. And apart from the interrupting the process and reversing the field, by decreasing the field to non-zero values and re-increasing it, we still have achieved a minor loop. So the retentivity, the remnants that we observe corresponds to that of the minor loop in this process. So let's summarize what we said. Well, we're looking at the magnetization curves of ferromagnetic materials. If a small applied field is sufficient to produce saturation, for example in A, we have a soft magnet. So A is an example of a soft magnet, whereas C requires a very large field to saturate, so that's a hard magnet. Magnetically soft materials like permalloy, magnetically hard materials like neodymium iron boron, permanent magnets, can be given as examples. Now, beyond saturation, Ms value is a constant. However, the magnetic induction will still increase with some slope because dB/dH is 1 in CGS or mu in SI, so it doesn't need to, well, it is not going to be a constant value beyond saturation. So if you look at the complete magnetization curve of a ferromagnet starting from a demagnetized state where the magnetization is zero, increasing the magnetic field to saturation, we have the saturation magnetization obtained with the corresponding saturation magnetic induction, and once again beyond this Ms is constant, Bs is not, as you can see. The magnetization curve from the demagnetized state to the saturation, that's the red curve, is called the normal induction curve. And sometimes in CGS units we plot, instead of B versus H, B minus H, which is intrinsic induction versus H. And if we then reduce the H to zero, we see that there will be a non-zero magnetic induction Br in the specimen that is called retentivity or residual induction or remnants. And if H is then reversed so that B will become zero, that's at this point HC here, we have the required magnetic field to do that is called coercivity or coercive force, and that is not the same thing as the field required to reduce M to zero. If you want to reduce M to zero, it's called intrinsic coercivity. After negative saturation, if we follow this purple path and go back to positive saturation, the loop that we have traced out is known as the major loop or major hysteresis. If we interrupt the process at any intermediate value and change the direction of the magnetic field or reverse the field, then we can trace out these minor loops. And there might be, for example, for this one, which is symmetric around zero, a coercivity and remnants field corresponding to the minor loop that we have traced out.